Hello everybody and welcome to my presentation. My name is Nadine Maier and I'm a PhD student at the Technical University of Munich at the chair of metal structures. Today I talk about influences on the buckling behavior from imperfections of different launching bearings. At first I explain the backgrounds that lead to this research project and my own experimental investigation. So during the incremental launching, large bending moments and support forces occur as a result of the cantilever above the last pillar. This results in a biaxial stress state in the web and due to the shear flow and inclination of the web, also in the bottom plate. This is usually the decisive load case for the buckling check. Additionally, during the incremental launching, the webs of the superstructure and the launching bearings often don't share the same center lines. The eccentricity can be caused by imperfection in the production process, misalignments of the launching bearings, the necessary air gap to the lateral guide, as well as the different thicknesses of the web along the superstructure. Two types of bearings are used for the launching. On the left, an example of a launching rocker system is shown. For this type of launching system, the launching beam is supported on a rocker bearing, which you can see here. Such a rotation phi y is possible. There is also an elastomer on the launching beams for a constant load introduction over the whole introduction length. At the right, a launching system using hydraulic checks is shown. Here the launching beams are supported on a spherical bearing which supports on the head of a hydraulic check. This allows a more flexible application of the system while always guaranteeing the necessary load introduction length into the superstructure. But this causes rotations phi x and y. The important question that arises is, does an eccentric load introduction influence the buckling behavior for one or both types of launching bearings? To answer this question, I carried out a series of tests. For this, I have developed our own test setup, which can introduce biaxial stresses into the specimens. You can see it in the picture and also in the figure below. The dimensions were chosen in order to test specimens with real dimensions to take into account real imperfections from the manufacturing. The external dimensions of the test setup are 8 by 11 meters. This allows to introduce a normal force F1 of 4.3 meganewton, a transverse force F2 of 8.6 meganewton, and a bending moment My of 34 meganewton meters into the specimen. In total, 12 specimens were carried out. The dimension of the web were chosen with 3 by 4 meters and the thickness with 8 millimeters. Parameters which were investigated are the stress ratio sigma c to sigma x, different bending and torsional stiffness of the longitudinal stiffeners and their distances, and what is particularly important for the topic of this presentation, different bearings and eccentric load introduction of the transverse load. Based on the experimental results, a numerical model was validated and an extended numerical parameter study was performed. The numerical model and the results of a few interesting parameters are presented in the following. The numerical model was created with the finite element program ANSYS. The material is defined as a bilinear material curve with the yield strength from the material certificates for the recalculation of the tests and 355 Newton per square millimeters for the parameter study. The tangent modulus is set at 1450 and the Young's modulus at 210,000 Newton per square millimeters. The load is applied through two external points coupled to the corresponding surface of the specimens via beams with equivalent stiffness of the test setup. The degree of freedom phi x of the external points f and g, for the load introduction of the transverse load depends on the examined lunging bearing and is free or fixed. As elements, shell elements with 4 nodes and 6 degrees of freedoms with a size of 2.5 millimeters were used. The contact between the lunging beams and the plate is defined with a coefficient of friction of 0.2. The imperfection is taken as the first buckling mode and its amplitude is scaled according to Eurocode 3 Part 1.5 Annex C. A very important detail is the modeling of the load introduction. For the hydraulic system with spherical bearings, the external point for the load introduction is placed in the center of the rotation of the spherical bearing. You can see it at the left. Therefore, the external point is located closer to the superstructure. The external point is connected to the surface of the lunging beam. The rotation phi x is free. This model is called M1. The second model represents the lunging rocker system. Here the external point is modeled at the height of the lunging beam and again connected to the surface. The rotation phi x is fixed. The model is called M2. The recalculation of the tests provides good results. For the following parameter study, I will now explain the names of the parameters and the model names. The name of the model is given by the investigated parameters. You can see an example here. For this presentation, it is only necessary to know that M1 or 2 identifies the type of the lunging bearing, EF stands for local buckling and GF for global buckling. Then comes the parameter S. You can see it here at the right side. S describes the distance between the external points for the load introduction to the superstructure. And beta is the stress ratio sigma C divided by sigma X. E is the eccentricity of the load introduction, which is varied between -30 to 30 millimeters. Here you see the influence of the different lunging systems on the base of the different boundary conditions phi x at the external points for the load introduction. The diagrams show the load factor as a function of the load eccentricity. The load factor for the model with S is 300 and E is 0 is selected to be 1.0, once for global buckling at the left side and once for local buckling at the right side. In both cases, it can be seen that an eccentric load introduction has an influence on the load capacity using hydraulic bearings. In case of the lunging rocker system, the eccentric load introduction has no influence. The lines are horizontal. It is interesting that in case of local buckling, a difference between the two systems is already detected at E is 0. This is due to the different boundary conditions and the associated buckling length of the first single panel. Here the results of the investigations of the distance S of the load introduction are presented. The diagram shows the load factor as a function of the load eccentricity again. The distance has little influence on the model M2, which are the horizontal blue lines. For model M1, it can be seen that the load factor decreases with an increasing distance S and the influence from the eccentricity grows. For example, you can compare the black lines. In the next step, S is varied until the influence from the eccentric load disappears. In the diagram, S is varied from 0 to 300 millimeters. It can be seen that the load capacity becomes smaller with large distance S, even without eccentric load. With smaller distance S, the load capacity keeps almost the same and also the influence of the eccentric load disappears. This is noticed for S between 7.5 and 30 millimeters. This effect can be described and is shown here. The rotation results in a torsional moment mx. Without eccentricity, this depends only on S. The case is shown on the left. On the right, you see the equation for mx with eccentricity. When mx becomes 0, there should be no influence from the eccentric load introduction. This is valid for S equal to minus E divided by 2 phi. At next, the influence of the stress ratio beta is investigated. The stress ratios 1 and 2 at different distances S are compared. The results are shown in the diagrams. In the diagram on the left, it can be seen that for both cases S, the load capacity becomes smaller with larger beta. This is due to the fact that the buckling results from the transverse load, and this is more dominant with a larger stress ratio. If you look at the diagram on the right side, you can see again the representation via the load factor. The model with S is 300 at E is 0 is selected as 1.0 for both stress ratios. The curves show that the influence on the eccentric load introduction is the same for both stress ratios, and the lines are congruent. Now I come to the summary and the outlook. It was determined that an eccentric load introduction has an influence on the buckling behavior by using open girders with hydraulic bearing during the incremental launching. With an eccentric load introduction, the distance S has an influence on the buckling behavior by using open girders with hydraulic bearing. Closed girders have not been investigated yet. A better load bearing behavior is expected. Due to the higher rotational stiffness of the bottom plate, the influence of the eccentric load introduction will become smaller. Previous recalculations according to Eurocode 3 Part 1.5 and Eurocode 0 show that the results are on the safe side in most cases, although they are influenced by the eccentric load introduction. More detailed results will follow. The results presents a part of the final investigations on the influence of the eccentric load introduction. All results have been checked with regard to the existing safety level and are currently being evaluated and analyzed. Results will be published at the end of September in the final report of the IEF with the EGF number 20455. Finally, I would like to thank the promoters of this project, the IEF and our project partners, Mrs. Kuhlmann and Mr. Protostadt from the University of Stuttgart. A special thanks also to the support of the named companies. I'm at the end of my presentation and thank you for your interest and your attention. If you have any questions, please feel free to contact me.